We're observing on the Keck telescope. I'll show you a picture of what it looks like. So it's these telescopes that are on the summit of Mauna Kea, and they're attached to each other by a corridor. Yeah, this is a nice view. Can y'all see this right here?
Yes, yes.
So there's this it's pretty long. I want to say maybe, is it 200 feet, the corridor between Keck 1 and Keck 2? 200.
Yeah, it's a couple of,
Yeah, so
yeah, we're going.
all right, thank you so much. So we're waiting for the target. So we are on the Keck that is would you say it's kind of at a diagonal, right? It's like
Yeah.
points northeast. And so the way that we're pointed, we have to wait a little bit for our target to rise before we can point towards the east. So this is a sky chart, star track chart of the current night sky at the current time. So it's about to be 8 o'clock local time in Hawaii. And our target is located right here. This is the Interstellar Comet. And it's just about this a white shaded region right here represents the Nazimuth structure of Keck. So we have to wait for that to clear. And once that is clear, we can point the telescope over in that direction. So Matthew is just Matt is operating the telescope. He is pointing the telescope in the direction. So this is a special view showing the operations of the telescope and when it is moving and where it is pointing. This window right here tells us where the telescope is pointing, and this magic Q guider is showing us the location in the night sky, an actual image of the night sky. So John O'Mara requested some guide cam images. Is that what he is referring to, Magic Cube?
Yeah, exactly. That's what he's referring.
Ah.
1, 2. Oh God, with the crowded fields.
Yeah. So
1, 2, 3.
So I can show everyone where the object is located in the night sky. So this is a star chart, star map, and this crosshair is where the object is. I'm going to move out to a couple degrees wide. So here's the galaxy, and the object is right here in this purple crosshair. And when we zoom in, it's just a lot of stars. So this is a field of view to about 2 by 2 arc minutes. You can see it's quite crowded with stars. And we're observing on a large telescope, so everything pops out here.
Stars.
Lots of stars, but the good news is that we're observing in the infrared, so stars tend to be a bit fainter in the infrared compared to the optical, so it may work out.
We're actually starting to. I don't know.
We have to wait for the guiding.
Stuff.
Yeah, we have to
make sure that's correct. So give me a minute here to get you lined up. Gotcha.
Thank you so much. So I'm going to get the exposure entries in here. So this is actually going to be the still. Let's see here.
Okay.
So
1, 2, 3.
yes.
1, 2, 3. 1, 2, 3. 1, 2, 3.
So we're taking some still images. Normally this comet is moving about 1 arc second per minute. That's pretty fast. Normally you would track.
Sorry, are you taking pictures first?
Are we ready?
No. I'm doing a quick pointing check.
Okay, thank you so much. So we are taking some pictures of the stars in the field so that we can map the contribution from the nucleus inside the coma.
And telescope around right now, just so you know.
Okay, I won't do anything.
Yeah.
So So Matt is getting the telescope ready for us. And this is a very crowded star field, so he's trying to find a star that he can use as a guide star. And he's doing a pointing check to check on the accuracy.
Okay, that looks good.
Also, Bryce, you remember that there's like a optimal order for the filters in terms of observing, because you want to it takes time for the filter wheel to move, and I think I gave the order in which it's optimal to sort of go through the filters one by one.
Right.
First, target field is your Moss Fire, and then hang on for a guide star. That's a double. That's a good one. You may file and ready.
Okay, so we're going to start off in Y. We're just going to keep it organized here. And we're going to do an integration time of 10 seconds.
Cool.
And we're going to do a test exposure first. So we're just going to, would that be stare? Leo, would that be stare if we just want to do a single test exposure?
Yes, that's correct. It's just stare if you just want to give one in.
So we just want to check the field, check the asterisms to make sure that we're looking at the right place on the sky. So it looks like we have changed to Y band, and I'm going to hit go, and we're going to take some data. Let's see what happens. So I got my field here. I'm going to check the pattern in the sky just to make sure we're in the right place. So this is Y band, so we should probably, okay, there we are. So this is the image right here. As you can see, it's quite full of stars. So let's zoom in a little bit. Let's see, is it possible that zooms out? So I think I can see the asterisms. There's a lot going on here. There's tons of stars, but the thing is that you look for all the bright ones. So I think I can recognize this asterism right here, and I can recognize this asterism right here. So this bunch right here is this bunch of stars right there, and these stars up here are these stars up there. So I think the comet's somewhere around there, and we're gonna take we're gonna do a box 9 because this looks pretty good. We have tons of stars. So I'm going to click on just want to say one person on the controls at a time, please. So we do not have conflicting things going on. So I'm going to click on box 9. And when I say box 9, repeat 1, that's going to just do one box 9, right, Leo?
That's correct. There's going to be a dither pattern of 9.
Okay, all right. I'm going to hit go here.
And Bryce, for reference, the optimal order is J, Y, K, H. So if we're starting with Y, we should go to K, then H, then J.
Yeah, that's good. That's a good thing to keep in mind. But because we're just going to go through each filter once, just for sake of simplicity, I'll go in the order that I see here in wavelength order Y, J, H, K. Yes, for certain, and we'll keep that in mind in the future. When we're doing rotationally resolved things.
We're in Y right now.
I'm sorry.
We're
Yes,
in Y
we are
right
in
now.
Y right now.
Cool.
Okay, so that was the first Y band of that box 9. We're just doing 10-second exposures here, very shallow exposures, because we just want to get a taste of what the point spread functions are like. There we go. So I'm going to do a diff here. So yeah, the diff brings out all the stars even more. Because you're doing a dither and you're subtracting each image from each other. So you're moving all the sky portions. So that's why you see white and black stars there, because the black stars are the negatives. So you dither and then you subtract the two images from together. So you remove the sky component, but because you still have that star in the second image that you're subtracting from the first image, you get a negative residual where the offset occurred. Okay, so this is going pretty fast. I'm not going to attempt to locate the comet quite yet. But we are in sidereal mode anyways. But my ephemeris is telling me that it is somewhere located around here. All right. So where are we on the box 9? So we have, let's see.
7.
Yeah, we're almost finished with the Y. Then we'll go to the J's. Then we'll go to the H and the K's. So just for reference, Y is the shortest wavelength filter we can get with this instrument. It's 1 micron. It's on the border between the visible and the infrared. So we're taking it so that we can connect our observations in the infrared with the visible. All right, here we go. Here we go, moving to the position 9. All right.
Fun story, Bryce. You know who invented Y band?
I do not know. Was it Jelko?
Brand. And, over here at Keck.
Oh, it's Lynn Hillenbrand. Wow.
Yeah, yeah. She has a paper from 25 years ago where it's where she comes up with the term Y band.
She built it herself?
She's my grand advisor, so I have like a special. She's my great so she was my advisor's advisor. So
She didn't build it, but she was the first to characterize it. She's the one who sort of came up with the conception of why we need a Y filter. But yeah, interesting complex story.
I'm going to keep the integration here
So badass.
at 10 seconds. So I'm moving to J band. I'm going to keep the integration at 10 seconds because that is the maximum amount of time we can take in J band. It looks like the slew has finished. I'm sorry, the filter change has finished. So I'm going to click go here. But for H and for K, we will have to adjust the coads and the integration times as to not saturate the detector with sky. Because the sky is much brighter in H and K. So just a little for reference here, J is about 1.25 microns, H is about 1.6, and K is about 2.2. So the longer wavelength you go, the more heat you have from the ambient environment. So let's see here. So these look like the J's are coming in here. And of course, lots and lots of stars. J is a bit more sensitive than K. This is an infrared optimized. So yeah, that's why you just full of stars there. I'm tempted to try to go in and look in there, but I think we're going to have to wait for the non-sidereal to take a look. So let's see where the comet is at this time. So it is 11th of July. 10 minutes. So this is JPL Horizons. It calculates all the positions of all the asteroids and comets. So it's doing decimal degrees here, so I'm going to change it to sesquimal. And so we have 612. All right, so part of the reason we're doing this is we definitely do want to show the audience what it's like observing an interstellar comets. But it's also to show how astronomy is done. I got to reset everything now because I accidentally closed that VNC window. All right, I'm going to reset everything. How many, where are we in the box 9?
7 out of 9. I'll look to 8 next.
Thank you very much. I'm resetting right now. Yeah, it's these little icons right here. If I click in the middle, it closes the window. Sorry, y'all. All right. So I'm gonna reopen everything. The data look fantastic, by the way. Overwhelming amounts of stars here. Yeah, it's that line from Space Odyssey. It's full of stars.
My God, it's full of stars.
Yeah, it's a lot of stars. It's a lot of stars. Yeah, and see when you do the difference, it makes it pop out even more. So I think I can see the comet. I'm not going to try to zoom into it yet because it changes so much so quickly. Matthew, I got it now. Oh, you got it. All right, thanks. Thank you. So for the H, we're going to have to lower the integration time to 3 seconds. And we'll do 4 coads. All right. So it looks like H has finished moving. It looks like it's finished moving. So I'm going to click on the box 9. Here we go. We're going to get some H-band imaging. There's also telluric features in the vicinity of H-band and K-band that make observing more difficult in these wavelengths. But they're the most scientifically interesting because the reason why it makes them so difficult, why it's so difficult to observe is because they're susceptible to water. This is where water absorption and emission occurs in our atmosphere. But it's also the most scientifically interesting because this is a way we can detect ice on the comet. We're going to be using these observations in these wavelengths to look for ice. So ice in a comet from another star. Yes. Someone says aloha from the Hilo stargazers. Aloha, Vani. I hope you're doing well.
We have someone from the Philippines as well.
Oh, hi.
Yes, Samuel.
Hello, Samuel. Don't be shy. Feel free to ask us questions or if you have any curiosity about what you're seeing.
Yes, everyone's comments and questions come to me and I share them with the group. So yes, everyone who's with us, please don't hesitate. I will share them with Bryce and Matthew and Laura May.
Thank you, Jamaica. So we're about halfway through these H's. There we go. Yeah, there's the asterism right there. So it's got to be somewhere around there in that vicinity. So let's look up 620. There we go. So the asteroid is moving west. Sorry, the comet is moving west, due west, at about this angle right here.
Exposure complete.
All right, so we should be about ready to change the K. K is also very strong. This one of the strongest filters in this this instrument. By the way, for context, this is the strongest near. This is the most powerful near-infrared camera on planet Earth.
I did not know that.
Yes. So that's why we're being overwhelmed with all these stars here. It's a very, very crowded star field.
We do have a question about what's the benefit of taking observations in these different filters?
Yeah, so H and K allow us to detect ice in the comet. And Y and J give us some indication of the color. Oh, Matthew has a comment in there.
Perfect.
All right. So we're going to do K after this. Let's see. I'm going to update this to all right. I am going to, after this exposure, I'm going to change the filter to K.
Exposure.
All right. I'm changing the filter to K. And I'm going to do 6-second integration. We can integrate a little bit longer in K. And 2 coads. We'll wait for the filter to stop. All right, the filter has stopped. All right, we're going to click go.
Bryce, you want to talk a bit about the nucleus?
Nucleus, yeah.
Whatever. Asking about that.
Oh, okay. So how large of a nucleus? Well, let's say comets are like cats. So comets kind of have fur in the form of coma. Coma is a cloud of gas and dust that surrounds the coma. Sorry, that surrounds the nucleus, which obscures the nucleus. So they're like a cat. You can have a cat that is obscured by its fur. Now the question is, if you see a big fluffy cat, is it a small cat with lots of fur, or is it a big cat with short fur? It's a very similar question for the comet. We don't know. When we look at a comet and we see its coma, we don't know if it's a big comet with a small coma, or it's a small comet with a big coma, because the dust obscures the coma. So what we have to do is we have to get high resolution observations, which allow us to look very close as possible to the nucleus in the coma in order for us to constrain just how large the nucleus is. The best instrument that we have for this in visible wavelengths is adaptive optics with Keck. We can use basically a mirror that can deform itself to counterbalance the distortion caused by turbulence in the atmosphere. And this allows you to get a very sharp image. You can also observe in space where you don't have the obscuration caused by the atmosphere, which allows you to get very, very sharp images. You can also observe in longer wavelengths, in thermal wavelengths that have the capability to see through the dust, because when you look at a comet, you're only seeing comet dust as small as your wavelength of light. So if you're looking at a comet in micron wavelength, you are looking at micron-sized dust. But if you look at longer wavelengths, let's say you go to millimeter sizes, like you use ALMA, you can observe the comet, and the dust that is smaller than about a millimeter in wavelength will be invisible. So you have the capability to directly image the comet, or as a way to get an X-ray to look through the cat's fur and just see the cat inside the massive fur. I made a cartoon of this at some point. Oh, I have to reset my my VNCs because it's doing that weird close thing.
We're almost done with the exposures, Bryce. Should I move to the sequence of doing?
Yeah, so use the one that is, so you don't use still, but do Atlas for 630. Actually, go ahead and do 620. So go ahead and highlight that. And Matt wants no, not still. Please not still. Okay. Matt, can you please slew to our next target? It's 3i Atlas.
Be like 5 seconds.
I'm watching your VNCs. Don't worry, Matthew. I got you.
Yeah.
Thank you.
I gotta keep an eye on the dark too. It's a pretty bad.
Okay, all right. So I'm gonna put on quick dark. Do I need to go to quick dark? Matt?
Yeah, quick dark should be fine.
All right,
Sounds good. Yep.
I'm gonna go to quick dark. Okay, so feel free to,
Fine, but this is a really crowded field, so I just don't want to risk it.
that's a good idea.
Yeah.
So this is, we're gonna change the target name to 3i moving.
Do you want me to recheck? I mean, this is really, it's super close, right?
Yes.
But so pointing should be close enough. Turn dive off, stop dive.
All right.
Dark. Slowing to 620.
So we're gonna start off.
Like that, a little bit to the right. Okay. Gonna grab another guide star on target here, right here, and you guys are good to start acquiring. Whenever you're ready, go ahead and get both the back set up.
All right, I'm gonna click on Y band.
Matthew, oh, sorry.
We're gonna just talking about. Yeah, what's up, Bill?
Do you want to take the screenshot or should I?
Once we actually know where it is and get it, let's just get a bunch of them. You get them, I'll get them, and then whichever
Okay.
best John will take. Yeah.
Yeah, I couldn't pick out which one it is at this point.
Yeah, no, I think I know where it is, but we'll double check with Bryce once we get him over here. Yeah.
All right.
Sounds good.
So we are going to be integrating for about 30 seconds between each exposure. The object's moving about 1 arc second per minute. So if we have half arc second seeing, the stars might look a tiny bit trailed, but probably not that much. Okay, so we have stopped slewing. We have we have 30-second integrations, and box 9, I'm going to hit glow. Here we go. And this time we are going to hunt for the comet. We are going to zoom in and look in the DS9 for the thing.
Cool. That'll be helpful, Bryce. Thank you.
I have a feeling that we're going to see this pretty well.
Yeah, me too.
All right, so I'm going to go to 6:30 here. I'm going to pull up the star chart. All right, so it's moving in between these two bright stars, and it's a little bit to the right of those. So we have just finished our first exposure. Now we don't have the difference image yet. We don't have the benefit of that, but we can still look for it. Yeah, so I see the asterism right there. The asterism in the data is right there. So it's somewhere in here. I'm going to try to zoom in. I think I see it. I think it's that thing right there, but it could be on top of a background star. Yeah, a little fuzzy wuzzy. Yep, that's it right there. It's,
Mouse like pointing at it. Yeah.
can you see it?
Wow.
Got a little. Oh,
All right, well, now we can do the difference image. So that will potentially make it pop out or confuse us because there's just so many stars.
Stars.
But I can see the asterisk. Yeah, it's right there. Yep, that's it right there. Does everyone see where my pointer is?
Yeah.
Can y'all
Definitely.
see it?
Yes.
So I'll try to get a better view of it here. I'm gonna zoom in a little bit more. Yeah, that's it right there. If it will let me align, let's see if I can move this out of the way, the chat window. Oh, it did an exposure complete again. All right. This is fun. All right, here we are. All right, zooming in a little bit. Here we go. Yeah, that's it right there.
Yeah, it's a little bit of drip too. You can see it moving.
Yeah, that's it. That's the comet right there. I'm pointing at it with my pointer, and you can see in the upper right-hand corner here in this little postage stamp, that's it right there. So it's got a compact little coma, just a tiny little coma. But we have the highest resolution pictures of it so far.
Comet here much more clearly than on any other image we've taken so far.
I could probably make a video of this, right?
Yeah.
Sort of like, right?
Yeah, DS9 has a built-in functionality for making GIFs.
Right? Yeah, yeah, yeah.
Yeah, you can make you can do blink.
That'll get Johnson funding through that.
Well, I think they I think NASA appreciates Keck a lot. So let's see here.
Exposure complete.
It is a workhorse of science. Yep, there it is. It's moving. It's trucking east. All right, sorry, trucking west. So I'm gonna try to zoom in a little bit more here so we can get a better look at it. Yep. Yeah, there it is. So it was a little bit to the left of the star. Oh no, it was a little bit to the left of the star, but now it's to the right, to the right.
Yeah, you definitely can clearly see that it's moved. Oh, this is so exciting. Wow.
That's the interstellar comet.
We would be conflagrating it with the star that's right next to it, right? So like the fact that the seat's good is allowing us to do these observations.
Oh yeah. Oh yeah, for sure. Yeah, it's Mauna Kea is a very special place.
Indeed it is.
Bryce, now that we're doing imaging, do you want to try doing the optimal filter sequence thing? I can keep it in my head.
No, it's okay. I just prefer to. It's not crucial. And then for this for simplicity and not potentially forget leaving a filter out. It's for lots of filter changes, for doing lots of things over time. I think it's definitely worth it. That's something we can write a script for.
It's 1 gauge beta TTL they have.
Yeah, I wrote one last time I was at Keck HQ. Josh worked on it with me, and we got it. Oh, there it is. It's moved. Ha 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 ha.
Exposure complete.
All right, that's fun.
Can you put your cursor on it again, Bryce?
I will try. I will try.
Oh.
Let's see here. We're taking images every 30 seconds, so it's by the time I find it, a new image pops in, and I have to look for it again.
Oh, okay, no worries.
But we definitely got it, that's for sure. All right, I'm going to zoom out a little bit so we can see more of the stars.
Exposure.
Oh, there it goes again. All right, so actually I need to change to K band. So sorry, J band. So I'm going to change to J, and we're going to do 3 coads of 30 seconds. What is the team's overall goals with these observations? Our goal is to test the existence of ices in the coma of this alien comet, let's call it. We want to see what ices look like in a comet from another star system. We know quite a bit about comets in our own star system, but so far there's only been one other comet from another star system. So this is the only the second one, and so far it looks a lot different from other interstellar objects. Okay, 10 integration time, 3 coads, and yep, Comet Borisov. All right. This is going. Yeah. Well, another thing is we can always download the images later and we can like play with them and, you know, make them all look pretty.
For NASA.
Yeah, I might, with your permission, pull these FITS files and play with them as well.
Oh, yeah. Feel free.
Thank you.
Could we get a copy of that?
Sure.
That would be super amazing. Thank you. Thank you.
Well, that's what we've been working on for like the last week or so. It's this comet. Okay, let's see. Let's take the difference image between the two J's and see how things pop out. Actually, did we finish the second J? No, not yet. We just finished the second J. So when you take the differences, it's not going to pop out because you're subtracting a Y from a J. So now we can. Let's see.
Sorry, can you tell me what the I time and coads were for J?
10 seconds and 3 coads.
Okay.
All right, here we go. Let's see here. Center image. Oh, here we go again. All right. So I am going to pull up the latest ephemeris, latest position. So it is 6:35. We'll call that 6:40. Whoop. And so that's well beyond this asterism. So now it's kind of in the middle of these 3 stars right here. And so we'll call those the three brothers. It's these 3 stars right here are these 3 stars in the image. And it's in line with the upper part of this cluster right here of stars. So it's somewhere around in here. I think I might see it. See if I can align. Uh-oh. It's challenging.
Might be that brighter thing.
It could be.
Yeah, because it's moved, I think, from the last one, right?
I think so.
Exposure.
Yeah, it's that bigger thing.
Let's see. Now, we're going to take the difference here. Oh, it likes to smooth it out. Yeah, I think it's right there. It's this blob. It's these 2 blobs. Can y'all see it up there in that little postage stamp up there?
Think so.
Yeah, it's kind of tough because we're zoomed out. And when I try to zoom in, we get a new image and I have to start all over again. All right, here we go. And because that's the rule with Keck, you don't stop taking data. You keep the ball rolling. And let's see here. Zoom out a little bit. I have to get my wits about me now. Oh, here it comes again. All right. Woo! Well, the good news is that we are still on that star field. We're still taking data. So that's all that matters, and that it's somewhere in this field. Have y'all ever played Where's Waldo?
Yeah, Bryce, you would be amazing at these spot the differences game.
Yes,
Like,
yes.
you might be a world
Oh,
champ.
there it is. Oh, I just saw it. Oh, wait, no, there it is. It's right there.
Right where
I
your
think
cursor
that-
is?
Do you see it?
Yeah, that's it.
Yeah, because it was merged with the blob, and now it's moved on to the
Yeah.
to the right.
Yes, I saw it then. I saw it for sure. Wow. Yes.
Where's Waldo Comet edition?
Waldo monochrome.
Yeah.
Yes.
Yeah, see, those books as a kid, it paid off. All those boring car trips where all you had was a Where's Waldo.
So, the I Spy and the Magic Eyes was my go-to.
Oh yeah. Oh yeah. Training generations of astronomers. All right. Okay, so we're gonna go to H.
Well,
So we're gonna go to integration time. 3 seconds. And coads 10. So comets they have different types of ices, or they can be ice rich or they can be ice poor. It's true, a lot of comets do have ice, but some comets do not. And if we do see ices, we want to not only say, okay, there's ice, but we can also say that there are certain properties about the ice. All right, so we have, I think we're done going to H. So now we'll take a box 9. So we want to start studying what the properties of ices are around comets and others around from other stars, and this is a unique opportunity to do that. Because when we look at other stars, we can only see the smallest dust particles, like little itty bits of dust floating around in space instead of dust from a comet, directly from a comet. Because when we look at other stars, we can only see very large structures. The ensemble of the dust creates a disk that is billions of miles wide. And we can see that with a telescope, but spotting an itty bitty individual comet around another star is about impossible. So we have to wait for the comets to come to us.
Exposure complete.
In the form of interstellar objects. Now this is going to be a challenge because this is H band. So I can see the asterism.
Just so we are planned ahead, what do you want to do for K band in terms of integration time codes?
So that's, yeah, so for K-band I use 6-second integrations, so we'll do 5
Okay.
coads because we want to keep the effective eye time at around 30 seconds for exposures.
Well, what's your eye time? Yeah.
Yeah,
The 5 coads is off.
yeah. For fainter objects, you take more coads. You don't increase the eye time. You want to take more coads.
Yeah.
But because this object is pretty bright, we can keep the number of coads lower. All right, so this is it. This is it right there, I think. Gotta wait. So it's just to the right of this middle star right here, and it's in line with this cluster of stars. So we'll wait for it to adjust itself and get in line. So I think we're gonna have to do a difference here. We'll do the difference and we'll see what happens once I do the difference. Okie dokie. All right, this is interesting. All right, so we have that group of stars right there, and we have one of these little things. All right, so I'm going to zoom in a little bit. I think I might see it. It's fainter in H band, that's for sure. Is that it right there? I'm not quite sure. So you think that's it?
Yeah.
Because there's no double. There's no double. It's a kind of a singleton.
I can see a shadow for everything else, so,
Ah, fantastic. So
you know, that harder H-band for sure.
so we're kind of shooting through the propeller here. So I would advise that we do this sequence again, Y, J, H, and K, because we want to get a decent amount of detections of the comet that aren't running into background stars. Crowded field photometry. It is not for the faint of heart.
Bryce, Matthew, Lorme, this has just been so thrilling, so exciting to join you as you're making these observations and to be able to actually see this comet in this incredibly full star field is just amazing. I am so thankful that we were able to shadow you all as you're using Keck to make these observations of this only our third interstellar visitor and second comet.
Well,
Exciting.
thank you so much for joining us on such short notice. It's fantastic. I'm glad you all got to see it. This is a pretty special event. The biggest telescope on the world, the most powerful infrared camera in the world, and only the third interstellar comet. So y'all are a lucky group.
That's right. Yes. Thank you so much, Joe, Samuel, Mickey, Vani, Benedicto. This has been wonderful to have you. I hope we see you in future sessions. Thank you for your questions. Bryce, so where can we find the results of your observations from tonight?
Well, we will be processing them, making them pretty images, and I can share those with you when we are convinced that they look good. It sounds like Matt wants to take a look at them as well. Our observer here, and we will be hopefully publishing these very soon. Yeah, we have an interesting data set, and so we need to publish it. So we have a paper, a paper about other observations that's under review in the monthly notices, the Royal Astronomical Society letters, that's based on optical data, and this will be a paper about the infrared data, and so. We will be happy to share the results with you when they are out, when they are public.